Okay, welcome to our Tuesday afternoon session with Deame, CEO of Nextera Video. And I think CEO is kind of a limited title for you. I mean, I know you're in charge, but also Jed really is the brains behind a lot of what, and the innovator, a lot of the really cool things that Nextera is doing right now. So he's going to talk us through NMOS 06. Not just NMOS 06, but everything that's in NMOS, and have us really understand why these new features are here, why we're spending time in the community developing them, and why people should be implementing them in their networks. So, Jed, take it away.
Great. Yeah, thank you very much, Wes. So, as you mentioned, Jed with Nextera, we're providers of IP cores for SMPTE 2110 and NMOS to help vendors get a jump start on their products. So today we're going to talk about what's new in NMOS and what's old and what's changed and how it really helps make this video over IP solution much more palatable and enhance value for our customers. So a quick agenda, we'll talk about the old stuff, and there are some new things with the old stuff, for 04 and 05, many of you may have heard of. We'll talk about what the gaps were, what was missing from the first round of what we thought might be good enough, and that kind of leads us into what's new, which is the ISO 8, 9, and the BCPs, which stands for Best Current Practice, and also the IS 10, which is authorization. So without further ado, we'll jump right into it. What is NMOS? Let's start with there, because maybe not everyone knows what NMOS is. It stands for the Network Media Open Specification, which was developed by the AMWA, which is one of the sponsors here, the Advanced Media Workflow Association. And the intent was to deliver an open specification to provide the software layers that abstract a lot of the complexities of ST2110 and present it in a manner where it can be actually easy to tie into any control system, any touch panel, and make it really just simple and seamless to use, as we've come to expect with SDI. So really the push-button simplicity, as can be seen by this photo from last year's IP showcase. Essentially, you just push a button, destination source, and through the magic of NMOS software, you're able to connect video sources to video destinations. So what does the NMOS part of it actually do under the covers? It's actually a set of APIs that connect the SMPTE 2110 controller, which is maybe a button panel or some control system, to the actual hardware of the 2110 device, which might be could be a camera, could be a monitor, could be a gateway, something that converts SDI or maybe even HDMI to 2110. So the pieces that are involved in here are what they call an API, an application programming interface, that exposes these resources, and they're named such as things like sources and flows, receivers, self, etc. That's how the outside world sees the NMOS, and it's actually a standard HTTP type transaction. So you can actually see this from a web browser. You can browse into an NMOS device, and you'll see these what look like folders, but they're actually resources that show you details about that particular device. And then the job of the NMOS itself is to interpret those commands that come in that might say switch from source A to source B or something, and interpret that and provide the low-level commands to the hardware to tell the hardware what to do. So again, an abstraction layer that hides the complexity of the hardware and makes it really simple to do basic things like switching. So how does it work? Okay, well, as I mentioned, it's an API, which is what software people like to call their interfaces, a simple exposed mechanism to control it. It is exposed via an HTTP. It's called a RESTful API, but it's essentially HTTP puts and gets. So it's the IP address of the card or the node that you're trying to address, and then there's a /xnmos, which says I'm an NMOS resource, and then the name of the API. So again, you could actually browse to any NMOS-enabled device with any web browser, IP address /xnmos. You can look at the node, you can look at the query resource within a registry. You could do channel mapping and see how it's all set. So that's that's basically how this is exposed to the operating system and to the control system. So a little more detail on how NMOS works, and some of you may not be totally familiar with it. In this example, we've got a couple sources here, which could be cameras, for instance, and we've got a destination, which could be a monitor. And the idea is we want to be able to switch these over IP. So first of all, how do I know what's out there? Right? In SDI, you don't really know. You just got source 1, source 2, destination 1. But in IP, we have the benefit of being able to know exactly what the device is we're talking to. So the way it works, the first step is each of these devices connect to this registry, which is some software running on a PC somewhere, and it identifies itself. It says, hey, I'm a camera, I'm this vendor, I've got this capability, I've got maybe 1 video channel and 16 audio channels. So everybody identifies themselves to the registry. It's kind of a map of the system. And then the control panel can actually come in and read this registry and see all the devices that are out there. And then it can actually automatically populate button panels or web GUI screens. So it could be very simple. It could be Sony camera number 1 or Ikigami camera number 2 in your control panel, and your display, program monitor 17, whatever it is. And when you do the switch, you push the buttons up in the butt panel. You say, I want destination 2 gets source 1. What it does is it sends a command to the receiver over IP, and it tells the receiver, subscribe to this stream, for instance, from this bottom camera. It says, I want to do an IGMP join to this stream, and then I want to do an IGMP leave from this stream, right? So it's really just telling this IP switch, this cloud is really just an IP switch off the shelf, and it's telling it, disconnect from this top stream and connect to the bottom stream. So that's basically how NMOS works. So what's new with this old part of it, which is the registration and discovery? So there's actually a new version out. It's called 1.3. It's published on the AMWA GitHub site. It consists of these 3 APIs, the Node API, Registration API, and Query API, which were those sort of folder-looking things under the web browser that I showed you a minute ago. So what's new specifically in 1.3 is this rightmost column up here, the check marks. You can see it does all the things that the older versions did, the core functions. One thing, it made the peer-to-peer mode optional, since that wasn't really widely used. It deprecated the connection management because that's actually taken as replaced by functions in ISO 5. There wasn't always an ISO 5, so it was needed in the beginning, but not anymore. And we added in some features for things like security, HTTPS and WebSockets, and 2022-6 flows, paged queries, support for ISO 5, the new connection management, ISO 7, which is more like a GPI over Ethernet, if you want to think of it that way, and the authorization signaling for security layers. So then there's ISO 5, the other old piece. So what's new with ISO 5 is, again, a new version, 1.1, as of September 5th. And again, this is the API that allows us to connect a sender to a receiver. So it's the magic software that does what we call activations, which is another way to say switching. One interesting thing is activations can be immediate, do it now, relative, do it in 30 seconds or a minute, or absolute. You could say 2 o'clock on Tuesday, I want to make this switch. So very powerful. And it supports things like forward error correction and redundant streams. So the new features in the latest release, 1.1, are things like telemetry transport and WebSockets, and also support for external parameters. So just a little more flexibility in where it works in multiple modes, in addition to the core functions like the RTP and the bulk and schedules that we talked about. So what's missing from ISO 4 and ISO 5? Most people have heard of those. I can register, I can connect, I can do my basic switching. Was that everything? Well, turns out not really, because especially if you compare it to an SDI environment, you could do audio breakaway in SDI. You could do de-embedding, embedding. Really powerful. We didn't really have a good way to do that a year ago. So the AMWA committee came up with a new standard called ISO 8, which I'll talk about, which gives us breakaway routing. We also needed a mechanism to have global parameters so that these smart devices could take advantage of that intelligence and know what system they're in. We'll talk about that. And then also security. Anytime you put something on IP, even if it's a closed network, you have to be concerned about security and even internal security threats. So we'll go through all of those. So first of all, audio mapping. So that's what ISO 8 is. It lets us map and shuffle channels within an IP environment. So you've got 4 new APIs, inputs, outputs, and the map, which connects the inputs and outputs together. And I/O is just kind of a convenient way to get everything in one access. And this gives us our SDI router-like capabilities to combine multiple channels. You could take channel 1 from source 1, channel 2 from source 2, and send them into an output. I've got a few examples of that coming up since this is a pretty interesting topic. So actually, this is what we showed at the IP showcase at NAB. We had a full demonstration, multiple vendors doing ISO 8. We had 3 16-channel senders and 2 16-channel receivers. And we had a GUI Control Panel that allowed us to take any number of channels from multiple sources. So this top, it's a little hard to see here, but these top 8 devices or audio channels from sender 1, and the bottom are from sender 2. And the top would be the SDI embedded channel output. So you can click on any of these buttons here and decide what audio channels you want to extract from each stream and embed those in your output. So very convenient, again, much like we had an SDI. So the demo we did at the IP showcase at NAB is we had 3 different sources with lots of different audio channels. It's a little hard to do an audio demo at a loud trade show, so we did it more graphically using these VU meters so you could see the levels of the different channels. So 3 different sources with different audio profiles. And the Nextera receiver here was actually just doing that inverse map that we just saw, that inverse diagonal line. So we're remapping channel 1 from this source to our channel 16 and channel 16 to our channel 1. So you can see the flip-flop there. And then the Imagine receiver was actually doing kind of a random mixture of all this. So again, a really powerful capability that really kind of finished out the basic functionality of what we need to switch IP and control it much like we do SDI. So then we said, well, how can we leverage this intelligence that we have to do more than what we did in SDI? Well, that's what ISO 9 is all about. It's called a system resource. It exposes a new API called System ID, but essentially it's a server somewhere in your system that's got information about how that system works. So it's got something like a system ID, which is randomly assigned at each facility. And this is pretty interesting. If you've got a board, an IP node, for instance, it's a receiver, and it powers down for whatever reason and powers back up, if it detects that it's in the same system it was in previously, it's like, okay, great, I'll just make that same connection I made previously. I was already connected to camera 1, I'll make that connection. But if it's not, if it's a different system, it's like, oh, I must be a new board, or you must have moved me to a different system, so I won't make that connection. So we can take advantage of this intelligence by having this global resource. We can also talk about, we can also specify in this whether it's secure or not. So HTTPS would be the secure version. We could indicate what NMOS versions are supported in the system. Do things like server priority to help with discovery, and also extensible with DNS service discovery, such as RDS. So we can tell all the nodes in the system what the IP address is of the registry, which is kind of nice. They can all find it without having to discover it. So those are more functional benefits. They're the IS numbers, which are more the specifications. We have another type of activity in AMO, which is the BCP, best current practice, which is a facility that allows us to recommend ways of using the standards in a certain way, the specifications, I should say, in a certain way for more flexibility. So BCP 002 is the grouping. That allows us to create natural groups between audio and video and metadata, for instance, that might all be separate streams, completely independent streams, but they're coming from the same device, so you might like to know that they all go together. So they use this group hint tag within the resources. An example here, you might have a video group 1, which is defined as playout master. So you could assign video group 1 into that playout master group, as well as audio group 1 and audio group 2. So you see that they all go together. And then you also have a role in addition to a group. So it could just be primary video, it could be audio 1 that's 2-channel, or it could be another audio that's part of a 5.2 mix. So convenient way to keep things together. Another example here, grouping based on devices in a gateway here on the left. Maybe grouping based on devices that are part of a playout group, etc. So very easy way to tag things and bring more intelligence to the system. So those are the functional improvements. We've also added security improvements, as we touched on earlier. How do we make sure that anytime we route a signal from A to B, we know it's an authorized route, we know that the user was supposed to be doing it, and it's not someone doing something we don't want. So this is another best current practice called BCP 003. It's got 2 parts to it. The first part is saying, let's just replace HTTP with HTTPS, just like you see in your web browser. When you go to your bank, you get an S there. That means it's secure. It's using a TLS, transport layer security, encrypted data. So you're actually sending this message that's AES encrypted using military encryption technology to get from A to B. Dash 02 takes it a step further and says, rather than just using a local certificate, I'll have an extra certificate authority in my system that already has, it's already been programmed with access rights for anyone on the system. And you have the ability to add and take away permissions. And then we've got IS-10, which builds upon the BCP 03. It specifies a little bit more detail on how that authentication server works. This is a bit of a work in progress, so we'll have more details on that next time. Essentially, it's just exposing an endpoint called register client that gives us access to tie this into existing systems. So I'll go a little bit into some more detail on the theory behind this. It uses a technique called PKI, public key infrastructure, which is a way that you can transport messages from A to B in a highly secure manner. It also gives you the rights to store and revoke privileges using public key encryption, which has been around for quite a while. But let's talk through how it would actually apply in a broadcast environment. So you've got your broadcast controller, of course, and your source and your destination that we're all familiar with. We're adding one new component called an authentication server. So the first thing we do is the broadcast controller makes a request to the authentication server using OAuth 2.0. It says, I would like to make a switch. And the authentication server says, okay, fine, I know who you are. You're an authenticated user. I'm going to send you back a token. It's called a JWT token, JSON Web Token. The broadcast controller then sends that token to the source and says, hey, I'd like you to start outputting a stream. The source says, oh, wait a minute, Leo, let me see if you're authorized to do that. So it looks at the public key that comes from the authentication server and sees it's good. Okay, now it turns on the stream and starts transmitting its essence flow. Now the broadcast controller sends a similar message to the IP destination. He authenticates it with the same public key, and if it's indeed authentic, then it subscribes to that stream. So now we're able to have a secure connection from A to B. So some of the core technologies that are used in this security scheme, we talked about PKI, also HTTPS, REST, which is this HTTP web-based put and get mechanism. JSON, which you may have heard of, which is essentially a text file that's got a combination of key value pairs. OAuth 2.0 is the open authentication scheme. And then JWT, which is the JSON Web Tokens. So the goals of NMOS really for security are as follows. We want confidentiality. We want to make sure if we're passing data between the client and the API that it's unreadable by anybody else. So no one knows what's going on except the devices that are talking to each other. And that we've identified that the API is interacting with a trusted party. The integrity is in place. it's clear that the data traveling to or from the API hasn't been tampered with. No one's jumped in the middle. They call those man-in-the-middle attacks. And authentication. So we can know that the packets came from the API that it's interacting with. This is a nice list of all the different security features. We're not going to go through all these independently, but anyone that's familiar with security and encryption might recognize some of these. AES encryption, we've got our Johnny Quest decoder ring on the right to decode some of these, but advanced encryption standard, which is the main encryption engine, the key exchange, elliptical curve, Diffie-Hellman, etc. So NMOS supports all of these. The minimum requirement is the one on the bottom, which is 128-bit encryption with elliptical curve key exchange. So what does it look like in a system if we actually implement this secure? This is a client that we worked with that was building a secure KVM, which is keyboard, video, mouse, all over an IP network. There's sources at the top, there's receivers at the bottom, and then the system manager in the center does control. So essentially what we're doing here is using these HTTPS control mechanisms to make sure that we're sending encrypted control messages to the receivers to have them connect to the transmitters. And we're also, interestingly, in this system, encrypting all of the sources as well, which is something that NMOS hasn't adopted yet, but at some point, if people need high-level security, this is for high-end control rooms. There are actually techniques that can be used to encrypt the video itself so that it can't be intercepted on the way through the system. So in summary, ISO 04 and 05 are solid, stable. They're out there, they work, they're mature. They're employed in most all new SMPTE 2110 products and installations. New features such as ISO 8 audio mapping, system discovery, and the BCP grouping really bring NMOS to a new level and provide the capability that was missing a year ago. So we've accomplished and also exceeded the capability of what previous SDI systems were able to do. The BCP03 security brings a sorely needed security layer into the system so that you can trust that the system is being controlled in a manner that it was intended. And and then the final point is that NMOS is really the glue that holds together these ST2110 systems and enables extraction of new business value. Thank you very much.
All right, Jed, thank you. So we have time for a question or two, if there's any from the audience. I had one question. So what do you see as the adoption level? I mean, from your perspective, obviously nobody can see everything that's going on in the industry. Of ISO 6, the connection management, is that, I mean, are people actively using that? Is it dynamic and growing, or is it one of those things that people only use if they absolutely have to?
All right, talk about ISO 5 connection management or the ISO 6 SDN piece?
The ISO 6, driving the software-defined network devices and things like that. What do you see? I mean, what from your viewpoint?
Sure, absolutely. Well, when we first started looking at building these large systems a while ago, a year or two ago, there were some concerns about whether IGMP, which is the traditional switch technology, could scale to very large numbers. So that's when this new technology was proposed, SDN, software-defined networking, which is essentially programming the switch and telling it that you want to have the switch route the signals for you. What we found is that there were a lot of tests done since that initial work that have confirmed that you could actually scale quite well with IGMP. So I think that removed some of the momentum from the SDN activities. Also talking to the switch vendors, it seems like they've de-emphasized that. So in our experience, we're seeing almost everybody is happy with the typical IGMP approach. And the reason they're adopting SDN is more to provide more of an automated setup mechanism so that when they're building their networks, they can build them out back in the factory, and then the installers can just download the setup into the switches. So There's a little bit out of it out there, but we're seeing for the most part it hasn't been broadly adopted.
Okay. Any other questions? All right. Well, thank you very much, Jed, and hope you had a good show.
Absolutely. Thanks so much.